Tonight, we are going to explore a concept that feels like it belongs in the realm of dreams or ancient myths, yet it is a hard reality written into the very laws of our universe. It is a truth that challenges everything we think we know about the steady, reliable passage of our lives. Most of us go through our days believing that time is a universal constant, a steady river that flows at the same pace for everyone, everywhere. We trust our clocks, our heartbeats, and the rising of the sun to mark the moments with absolute precision. We imagine that a second on Earth is the same as a second on the moon, or a second in the dark, silent reaches between the stars. But the deeper we look into the tapestry of the cosmos, the more we realize that time is not a rigid frame. It is soft, it is malleable. It is a fabric that can be stretched, twisted, and slowed to a crawl by the invisible hand of gravity. Somewhere out in the deep silence of the galaxy, there are objects so dense and so powerful that they can turn a single tick of a clock into an entire lifetime for an observer watching from afar. To understand how 1 second on a neutron star could possibly last years elsewhere, we must first set aside our intuition and look at the weight of the invisible clock that governs every movement in the universe. Consider for a moment the quiet room where you are currently resting. Perhaps you can hear the faint ticking of a clock on the wall, or the steady rhythm of your own breathing. Each of those intervals feels discrete and unchanging. In our human experience, a second is a tiny, flickering thing, long enough to blink, to catch a breath, or to let a single thought pass through the mind. It is the basic unit of our existence, but science tells us that this feeling of constancy is an illusion born of the fact that we live on a relatively small, gentle planet. We are tucked away in a corner of space where gravity is weak enough that we do not notice its influence on the passage of hours and days. However, the ground beneath you is actually tugging on the moments of your life. It is a subtle effect, far too small for our biological senses to detect, but it is real nonetheless. The clocks at the base of a tall mountain actually tick slightly slower than the clocks at the summit. The people living in the valleys are aging a fraction of a billionth of a second slower than those living in the high reaches of the atmosphere. This is the beginning of our understanding of gravitational time dilation. It is the fundamental law that states that the stronger the pull of gravity, the slower the clock will run. To grasp why this happens, we must envision the universe not as a hollow container where things happen, but as a physical substance called space-time. Imagine a vast invisible sheet of fabric stretched tight across the darkness. In a state of perfect emptiness, this fabric is flat and straight. A clock moving across it would tick with perfect regularity, but the moment you introduce mass, a star, a planet, or even a human being, the fabric begins to sag. The weight of the object creates a curve, a dimple in the very geometry of existence. This curvature is what we perceive as gravity. When you walk across the floor, you are simply following the curve created by the mass of the Earth. But mass does not just bend space, it bends time as well. Light and time must travel through these curves, and as the path becomes steeper and more distorted, the intervals between moments begin to stretch. It is as if time itself becomes heavy, struggling to climb out of the gravitational well created by a massive object. On Earth, this well is shallow, a mere ripple in the grand scheme of the cosmos. But if we were to travel to a neutron star, we would be stepping into a gravitational canyon so deep that the laws of physics begin to look like magic. A neutron star is one of the most extreme environments in the known universe, a place where matter has been pushed to its absolute breaking point. It is the remnant of a star that was once many times larger than our Sun, but has since collapsed into a sphere only about 20 kilometers across. To understand the scale of this, imagine taking our entire Sun, a glowing orb that could fit more than 1,000,000 Earths inside it, and crushing it down until it could fit within the boundaries of a small human city. The resulting density is almost impossible to comprehend. The gravity on the surface of such an object is billions of times stronger than what we experience here. If you were to drop a common object, like a small stone, from a height of just 1 meter above the surface of a neutron star, it would hit the ground in a fraction of a microsecond, accelerating to thousands of kilometers per second in an instant. This immense pulling force does not just affect physical matter, it seizes the very light that tries to escape the star, and, more importantly for our journey tonight, it seizes time itself. If you were standing on the surface of this cosmic titan, your local experience would feel perfectly normal. You would look at your watch, and you would see the second hand moving with its usual mechanical rhythm. You would feel your pulse, and it would beat in the way it always has. This is the strange beauty of relativity. To the person inside the gravitational well, time always feels like it is moving at the same pace. But the universe is a matter of perspective. If a friend of yours remained far away in the empty reaches of space, watching you through a powerful telescope, they would see something haunting and surreal. They would see you as if you were frozen in a deep, thick syrup. Every movement you made would appear to take hours, then days, then weeks. As you raised your hand to wave, years might pass for your friend in the time it took for your arm to move just a few inches. The light carrying the image of your gesture would be stretched so far that it would shift in color, turning deep red, and eventually disappearing into the infrared. For you, the wave was a fleeting moment. For the rest of the universe, it was an epoch. This disparity creates a profound question about what we consider to be the true age of things. If you were to spend just a few minutes walking along the scorched metallic crust of a neutron star and then return to Earth, you would find a world that had moved on without you. The people you knew would have grown old and passed away. Cities might have crumbled into dust and been replaced by new civilizations. The very stars in the sky would have shifted their positions. You would be a time traveler, not because you moved through a portal, but because you simply stood in a place where gravity was heavy enough to hold back the clock. You would have experienced only a few hundred heartbeats, while the rest of the galaxy experienced millions. This is the weight of the invisible clock. It reminds us that our experience of life is entirely dependent on our environment. We are tethered to the gravitational rhythm of our planet, and it is only because we rarely leave this home that we are able to maintain the illusion that time is the same for everyone. The physics behind this stretch is not just a theoretical curiosity, it is a reality that we have to account for even in our own modern technology. Global Positioning System satellites, which we rely on for navigation every single day, orbit about 20,000 kilometers above the surface of the Earth. At that altitude, gravity is significantly weaker than it is on the ground. Because of this, the atomic clocks on those satellites tick about 45 microseconds faster every day than the clocks on our phones and in our cars. While 45 microseconds might seem like an insignificant sliver of time, It is enough to throw off the accuracy of our location data by several kilometers within a single day if it is not corrected. We are already living in a world where we must compensate for the fact that time flows at different speeds, at different heights. When we transition our thoughts from these tiny shifts on Earth to the massive, crushing environment of a neutron star, we are simply looking at that same effect magnified to a terrifying degree. Imagine the surface of a neutron star as a place where the air itself is made of intense magnetic fields, and the ground is a lattice of iron nuclei crushed into a state called degenerate matter. There is no softness there. The pressure is so great that it overcomes the electrostatic forces that normally keep atoms apart. Electrons are forced into protons, creating a sea of neutrons. In this state, the star is effectively a single, giant atomic nucleus. When you have that much mass concentrated in such a tiny area, the warp in space-time becomes a sheer cliff. As you move closer to the surface, the slope of time gets steeper. For every meter you descend toward the center of that gravity, the outside world seems to move a little faster. By the time you reach the surface, the time translation between you and a distant observer becomes a vast chasm. This brings us to a beautiful and slightly melancholic realization about the nature of existence. If 1 second on that star represents years in the outside world, it means that the neutron star is, in a sense, a reservoir of the past. If you could see the light from the rest of the universe while standing there, you would see the history of the cosmos playing out before your eyes like a film being fast-forwarded at incredible speeds. You would see stars being born and dying in the time it takes you to blink. You would see galaxies rotating and colliding in a dizzying dance of light. The entire story of the universe would unfold around you while you stood in a state of near-permanent stillness. It is the ultimate expression of the deep silence that permeates the high-gravity regions of our space. It is a place where the ticking of the clock is so heavy that it almost comes to a halt. As we move forward in our exploration, we must ask ourselves how such a bizarre object comes to be. The universe does not simply create these time-warping giants without a reason. They are the leftovers of an ancient and violent process, a story of a star that fought against the pull of its own weight for millions of years and finally lost. To understand the frozen clock of the neutron star, we must look back at the life of the star that died to create it. We must look at the balance of power between the heat of nuclear fire and the relentless, patient pull of gravity. It is in that struggle that the ingredients for this time-stretching reality are forged. Every second that is lost on a neutron star was paid for by the collapse of a sun, a process that represents the most powerful transformation of matter known to science. When we consider the weight of this invisible clock, we start to see that the universe is far more mysterious than the clockwork machines our ancestors imagined it to be. It is not a set of gears turning in sync. It is a fluid, changing landscape where the very measurement of a moment is subject to the influence of the giants that dwell in the dark. The neutron star stands as a sentinel of this truth, a cosmic lighthouse that signals to us that our time is a precious, fragile thing, shaped by the mass of the earth beneath our feet and the stars above our heads. In the silence of the night, as you listen to the steady passage of your own time, remember that somewhere out there, a second is holding within it the weight of years, waiting to be understood. We are only beginning to scratch the surface of this strange reality, and as we look deeper, we find that the more matter we squeeze into a small space, the more the rules of the world we know begin to melt away, leaving us with a vision of a universe that is both terrifying and infinitely beautiful. This slowing of time is not just about the numbers on a screen or the ticks of a mechanical device. It affects everything. It affects the vibration of atoms, the movement of light waves, and even the chemical reactions that allow life to exist. If a biological organism could somehow survive on the surface of a neutron star, every biological process within it would be slowed down in perfect synchronization with the local clock. The firing of neurons, the folding of proteins, and the replication of genetic material would all occur at a pace that would seem like a standstill to the rest of the galaxy. It is a total immersion in a different speed of reality. This is the heart of what we mean when we talk about the invisible clock. It is not just that time is being measured differently, it is that the very fundamental refresh rate of reality has been adjusted. In the vast, lonely stretches of our galaxy, there are thousands of these stars, each one a localized bubble of slow-moving time. They are like anchors in the fabric of space-time, pinning down the moments and refusing to let them pass at the same rate as the emptiness around them. As we contemplate this, the world around us begins to feel a little more transparent. We start to see the connections between mass, gravity, and the heartbeat of the universe. We realize that we are participants in a grand gravitational symphony, and that our rhythm is just one of many. The weight of the invisible clock is a burden carried by the most massive objects in the sky, and by understanding them, we catch a glimpse of the true nature of the dimensions we inhabit. To truly understand how time can be so profoundly altered, we must look at the violent and awe-inspiring history of how these cosmic titans are born. A neutron star does not simply appear in the darkness. It is the bruised and broken heart of a giant that was once the pride of the galaxy. This is a story of a long, epic struggle between two of the most powerful forces in nature: the expansive energy of light and the relentless, patient pull of gravity. It is a war that every star must fight, and for the most massive suns, the end of that war is a cataclysm that defies all human comparison. By examining the death of these giants, we begin to see how matter can be crushed into a state where it no longer follows the rules of the world we know, and how that density creates the well of time we discussed earlier. Every star we see in the night sky is essentially a delicate stalemate. On one side, there is the incredible weight of the star's own mass, trying to pull everything toward the center. Gravity is a patient architect. It wants to collapse the star into a single point. On the other side, resisting this collapse, is the outward pressure of nuclear fusion. In the heart of a star, the temperature and pressure are so extreme that hydrogen atoms are slammed together to form helium. This process releases a staggering amount of energy in the form of light and heat. This outward radiation, pressure, acts like a pillar, holding up the massive weight of the star's outer layers. For millions or even billions of years, this balance remains steady. The star shines with a constant, reliable light, oblivious to the fact that its fuel is a finite resource. However, as a massive star, one at least 8 to 10 times larger than our Sun, ages, it begins to run out of its primary fuel. When the hydrogen in the core is exhausted, the outward pressure weakens for a moment, allowing gravity to squeeze the star even tighter. This compression raises the temperature even higher until the star begins to fuse helium into carbon. This cycle repeats itself several times, with the star burning through heavier and heavier elements as it desperately tries to maintain its internal pressure. Each new stage of fusion is shorter and more frantic than the last. Carbon becomes neon, neon becomes oxygen, and oxygen becomes silicon. To look at the interior of such a star in its final days would be to see a giant cosmic onion with layers of different elements all burning at once, each layer trying to hold back the inevitable. The final chapter of this life begins when the star attempts to fuse silicon into iron. In the language of nuclear physics, iron is a unique and dangerous element. For every element lighter than iron, fusing two atoms together releases energy. But iron is different. It is the most stable nucleus in the universe. Fusing iron atoms together does not release energy. Instead, it consumes it. Iron is the ash of the stellar furnace, a substance that takes but never gives back. When the core of a massive star is finally converted into iron, the furnace simply goes out. The outward pressure that has held the star up for millions of years vanishes in an instant. There is no longer anything to resist the immense, crushing weight of the star's outer layers. What follows is perhaps the most sudden and violent event in all of physics. In a fraction of a second, faster than you can blink your eyes, the iron core, which is roughly the size of the Earth, collapses. Gravity, having been denied for millions of years, rushes in with a fury that is almost impossible to picture. The core implodes at nearly 25% of the speed of light. Imagine a world as large as ours being squeezed down to the size of a small city in less than a second. The outer layers of the star, suddenly left with no ground beneath them, begin to fall inward as well, following the core into the abyss. As the core collapses, the density reaches a point where the very atoms themselves begin to shatter. Normally, atoms are mostly empty space. If an atom were the size of a football stadium, the nucleus would be like a small marble in the center, and the electrons would be like tiny gnats buzzing around the furthest seats in the stands. In our everyday world, atoms stay apart because their electrons repel each other. But the gravity of a collapsing star is so great that it overcomes this repulsion. It crushes the electron gnats right into the nucleus marble. In a process known as electron capture, the electrons and protons are forced together, turning into neutrons and releasing a ghost-like particle called a neutrino. Within a split second, the core of the star has been transformed from a complex lattice of atoms into a solid ball of pure neutrons packed together as tightly as the laws of physics will allow. This new core is what we call degenerate matter. It is so hard and so dense that it is effectively incompressible. When the outer layers of the star, which have been falling inward at incredible speeds, finally strike this wall of neutrons, they bounce. The result is a shock wave of such magnitude that it tears the rest of the star apart. This is a supernova, one of the brightest and most energetic events in the cosmos. For a few brief weeks, a single supernova can outshine an entire galaxy containing hundreds of billions of stars. It flings the heavy elements forged in the star's heart, the carbon in your cells, the oxygen you breathe, and the iron in your blood, out into the void, seeding the universe with the ingredients for future planets and life. But our focus tonight is on what remains behind. Once the fires of the supernova have faded and the debris has cleared, we are left with the core. This is the neutron star. It is a sphere roughly 20 kilometers in diameter, yet it contains more mass than our entire sun. It is a city-sized ghost of a dead giant. The density here is so extreme that if you could take a single teaspoon of this material and bring it back to Earth, it would weigh more than an average mountain. It would simply fall through your hand, through the floor, and through the very crust of the Earth, eventually settling in the center of our planet. This immense concentration of mass in such a small volume creates the warped space-time environment where time itself begins to lose its meaning. We often think of gravity as a force that pulls, but after a star has collapsed into a neutron star, we must start thinking of gravity as a geometry. The neutron star has curved the fabric of reality into a steep, narrow spire. The closer you get to the star, the more distorted the geometry becomes. It is this distortion that stretches a second into years. The light trying to leave the star is fighting against a gravitational pull so strong that it actually loses energy as it climbs away. This is why a distant observer sees the light of the star shifted toward the red end of the spectrum. It is also why they see everything on the star moving in slow motion. In the wake of the supernova, the neutron star also inherits the spin of its parent. Just as a figure skater spins faster when they pull their arms in close to their body, the neutron star spins with terrifying speed because it has collapsed from a massive size into a tiny one. Some of these stars rotate hundreds of times per second. As they spin, they often emit beams of intense radiation from their magnetic poles. If these beams sweep across the Earth, we see them as regular, ticking pulses of light, much like a cosmic lighthouse. We call these pulsars. For years, astronomers were baffled by these perfectly timed signals, even briefly wondering if they were messages from an intelligent civilization. But we now know they are the rhythmic heartbeats of dead stars, echoing through the vacuum of space. The environment on the surface of this newly born star is unlike anything else in nature. There is no air, only a thin atmosphere of plasma hugging the crust. The magnetic fields are trillions of times stronger than the magnetic field of the Earth, so strong that they would distort the very shape of the atoms in your body from a distance of thousands of kilometers away. The surface itself is thought to be a smooth, incredibly hard crust made of iron nuclei. But even this iron is not the iron we know. It is crushed into a crystalline lattice that is millions of times stronger than steel. Beneath this crust, the pressure continues to rise until the nuclei themselves dissolve into a fluid of neutrons, protons, and perhaps even more exotic particles that we have yet to name. When we look at a neutron star, we are looking at the final, desperate triumph of gravity. It has crushed the light out of a star, shattered its atoms, and bent the very passage of time. The star is a survivor of a war that began billions of years ago in the silent clouds of gas that first collapsed to form it. Every second that is delayed on its surface is a testament to the sheer magnitude of the energy that was released during its birth. It is a place where the ordinary rules of life are suspended. There is no weather, no seasons, and no change, only the steady, slow ticking of a clock that has been buried under the weight of an entire sun. As we dwell on the violence of this birth, it is important to remember that this process is necessary for the universe as we know it. Without the death of these massive stars, there would be no heavy elements. The iron in the core of the star is the same iron that carries oxygen through your veins. You are quite literally made of the remnants of stars that died in these cataclysmic explosions. But while we carried the elements away with us, the neutron star kept the mass, it kept the density, and in doing so, it kept the ability to hold back the river of time. It stands as a dark, silent remnant of a process that gave us life, yet it remains a place where life can never go. If you were to approach this star, you would not see a burning sun like our own. You would see a small, faintly glowing orb, perhaps shimmering with the intense heat left over from its collapse. But as you drew closer, the visual distortions would become overwhelming. Because gravity is so strong, it bends the path of light so much that you would be able to see the back of the star as well as the front. The star would appear as a distorted sphere, with its entire surface visible at once. And as the seconds on your watch began to stretch, the universe behind you would begin to accelerate. You would be moving toward a horizon where the present moment of the galaxy is rushing past you, leaving you behind in a frozen pocket of history. The story of the violent death of a giant star is not just a tale of destruction, it is a tale of refinement. The universe takes something massive and diffuse, a giant cloud of gas, and refines it through nuclear fire and gravitational pressure into a tiny, perfect diamond of pure matter. It is the ultimate expression of how nature can take the familiar and turn it into the alien. The neutron star is a monument to that transformation. It is a place where the energy of an entire sun is stored in a volume no larger than a city, and where the weight of that energy is so great that it pins down the fabric of space-time, refusing to let the moments go. As the supernova debris continues to expand outward into the galaxy, it will eventually cool and clump together, forming new stars, new planets, and perhaps new civilizations. Those new worlds will look out into the night sky and see the faint pulse of the neutron star, never realizing that it is a piece of their own history. They will measure their time by the rotation of their planets and the ticking of their atomic clocks, never suspecting that there are places in the dark where a second is as long as their entire recorded history. The violent birth of the neutron star is the price the universe pays for complexity. It is the cost of the heavy atoms and the vast spaces we inhabit. And in the silence that follows the explosion, the neutron star remains, a quiet, spinning reminder of the power that created us. We are, in a sense, the children of these explosions, but we are also the observers of their aftermath. When we point our telescopes toward these distant remnants, we are not just looking at stars, we are looking at the boundaries of what is possible. We are looking at the limits of density and the limits of time. The neutron star tells us that the universe is not just a place where things exist, but a place where things are transformed into their most extreme versions. It challenges us to imagine a world without atoms, a world without seconds, and a world where gravity is the only master. In the deep silence of the cosmos, the story of the star's death continues to echo, a long and rhythmic song of collapse and creation that defines the very shape of our reality. Imagine you are drifting in a vessel designed to withstand the impossible, suspended in the cold velvet darkness of the interstellar void. Ahead of you lies your destination, a tiny, shimmering point of light that does not twinkle like the stars you knew as a child. This is the neutron star we have been following, a silent giant that commands the space around it with an iron grip. As we begin our theoretical descent toward its surface, we are not just traveling across a distance of kilometers. We are entering a region of the universe where the very foundations of reality, space and time, begin to warp and stretch in ways that defy our deepest instincts. This is the journey into the surface of eternity, a place where every kilometer we gain brings us into a deeper layer of gravitational influence, and every moment we spend becomes more disconnected from the world we left behind. From a great distance, the star appears manageable, perhaps even beautiful. It glows with a fierce, steady heat, but its size is deceptive. Because it is so small, you could easily mistake it for a distant planet until you notice the way the stars behind it seem to dance and swirl. This is gravitational lensing, the first sign that we are entering a zone of extreme curvature. As we approach, the light from the background galaxies is caught in the star's immense gravity, bent around its edges as if passing through a thick glass marble. You are seeing the universe distorted, a carousel of light that marks the boundary of the star's domain. But the most surreal visual effect happens as we get closer. Because gravity is so strong, light from the back of the star is actually pulled around the sides and directed toward our eyes. We are able to see more than half of the star at once. We see the poles, the front, and the edges of the far side all at the same time. The star appears to bulge toward us, a golden, metallic orb that seems to wrap itself around our field of vision. As our vessel moves into the deeper reaches of the gravitational well, something strange begins to happen to the light entering our windows from the outside universe. Light falling toward a neutron star is like a ball rolling down a steep hill. It gains incredible energy as it descends. This is known as gravitational blue shift. The gentle, white light of the distant suns begins to shift toward the blue end of the spectrum. It turns violet, then ultraviolet, and eventually, the very starlight becomes a piercing rain of high-energy X-rays. While we are shielded within our imaginary craft, we notice that the universe behind us is growing brighter and more energetic. But it is not just the color of the universe that is changing, it is the tempo. We look at the monitors that maintain a link to our home, millions of kilometers away. On one screen, we see a clock on Earth, synchronized with the one on our wrist before we departed. For the first few days of our journey, the two clocks seemed to tick in perfect unison. But now, as the neutron star looms large, filling our view, the disparity becomes haunting. On our wrist, the second hand sweeps steadily, one beat at a time. 1001, 1002. We feel our pulse and it is calm. But on the screen showing the Earth, the clock has begun to spin. The second hand is no longer ticking. It is a blur of motion within the time. It takes us to take a single, deep breath. Hours have passed on Earth. By the time we have finished a simple meal, days have vanished into the history of the outside world. This is the threshold of the deep time dilation we sought to understand. We are not just moving through space, we are sinking into a pocket of existence where time has become viscous. To us, everything feels normal because we are moving with our local clock. This is the fundamental grace of general relativity. You can never feel your own time slowing down. You are always at the center of your own now. But as we descend, the definition of now for the rest of the universe accelerates away from us. Every meter we descend is like a year being added to the lives of those we left behind. If we were to stop our descent and hover just a few kilometers above the surface, we could look back and watch the entire future of the human race unfold in what feels like a single afternoon. We would see the continents shift, the oceans rise and fall, and the very sun eventually grow old and dim, all while we are merely waiting for our coffee to cool. The sensation of this descent would be one of profound isolation. You are still within the same universe, yet you are effectively separated by an invisible wall of time. As you look toward the surface of the neutron star, you see a landscape of shimmering, crushed matter. The star is so smooth that the highest mountains are only a few millimeters tall. Yet even those tiny ripples are formidable obstacles in such high gravity. The surface is a crystalline crust of iron, glowing with a temperature of millions of degrees. But because of the time dilation, the light emitted from the surface is red-shifted as it struggles to climb out of the well. From our perspective, moving toward the surface, the star appears to glow with a strange, unnatural intensity, while the universe behind us appears to be frantically rushing toward its end. As we get closer, we begin to feel the physical effects of the curvature. Gravity is no longer a uniform pull, it becomes a tidal force. Because your feet are closer to the star than your head, the gravity pulling on your feet is significantly stronger. In a less protected environment, this would result in a terrifying stretching of the body. But even within our ship, we can feel the geometry of space trying to elongate every atom. It is as if the universe is trying to pull us into the shape of a long, thin thread. This is the reality of spatiotemporal curvature. It is not just a mathematical concept, it is a physical weight that presses against the very essence of your being. You are becoming part of the star's twisted geometry. At this point, the time dilation reaches its most extreme. 1 second of our time is now worth years or even decades in the empty spaces far away. If we were to look through a telescope toward our home planet, we would see it as a flickering ghost, a place that has already moved on into a future we can never truly belong to. We are standing on the edge of eternity, where a single heartbeat occupies a vast stretch of cosmic history. This is why we call it the invisible clock. There is no sound to mark this transition, no feeling of being slowed down, yet the entire galaxy is passing us by. It is the ultimate expression of the deep silence. The star does not speak. It simply exists as a monumental weight that anchors the present moment so firmly that it cannot move forward at the usual pace. The psychological weight of this journey would be as intense as the gravitational one. How does a mind process the fact that every blink of an eye represents the birth and death of distant civilizations? There is a certain melancholy in being a passenger to eternity. You are a witness to the entire story of the universe, but you are a witness who is frozen in place. The neutron star acts as a cosmic time capsule. If someone could remain here for what they perceived as a year, they would return to a universe that was billions of years older. They would be an ancient traveler in a youthful body, a person whose life was measured in seconds, while the stars were measured in eons. This journey also reveals a strange truth about the nature of distance. In our everyday lives, distance is measured in meters and kilometers, but in the vicinity of a neutron star, distance and time become so intertwined that they are impossible to separate. To travel closer to the star is to travel further into the future of the outside world. The surface of the star is not just a physical destination, it is a temporal one. It is the place where the now of the universe is held in check by the sheer density of matter. We often imagine time as something that happens to us, but here we see that time is something that is created by the environment. It is a product of the mass and the energy around us. If we were to attempt to land on the surface, the forces would become truly incomprehensible. The magnetic fields, which are trillions of times stronger than Earth's, would begin to warp the very atoms of our vessel and our bodies. Electrons would be squeezed into elongated shapes, and the very chemistry of life would cease to function in the way we understand it. But even if we could survive, we would find that the surface of the star is a place of absolute frozen perfection. Because the gravity is so high, any atom that lands on the surface is immediately crushed into a perfectly flat layer. There is no dust, no air, and no movement. It is a world of pure, solid geometry, vibrating with the immense energy of its own weight. As we hover in this state, watching the universe age behind us, we realize that we have reached the ultimate limit of physical experience. We are in a place where the rules of the human world have been entirely replaced by the rules of the extreme. We see that time is not a gift that is given equally to all. It is a variable that depends on where you stand and how much matter is beneath your feet. The neutron star is a monument to this relativity. It is a place where the universe says that a moment can be an eternity, and an eternity can be a moment. It is a reminder that our human scale is only a tiny fraction of what the cosmos has to offer. The descent toward the surface is, in many ways, a descent into the mind of the universe itself. It is where we see the equations of Einstein come to life in a way that is both terrifying and beautiful. We see that the fabric of space-time is not just an empty stage, but a dynamic, changing thing that can be folded and pinched until the ticking of a watch is silenced by the weight of a sun. In this silence, we find a new kind of understanding. We realize that the now we cherish on Earth is a rare and precious thing, a gentle rhythm that allows us to live our lives in a steady stream. But out here, in the shadow of the giant, that rhythm is shattered. Looking back one last time before we conclude this phase of our journey, we see the outside universe as a frantic, distant firework display. Stars flash into existence and disappear in seconds. Galaxies spin like spinning tops. The entire history of the cosmos is a blur of light and motion. And yet, here we are in our quiet, heavy vessel, still living in the same second we started. Our heart beats once. Outside, a world has begun and ended. Our heart beats again. A new star has been born and died. We are the masters of a single frozen moment, while the rest of existence rushes toward the dark. This is the surreal reality of the neutron star, a place where you can hold a second in your hand and watch it last for years. The transition from the fluid, fast-moving time of the void to the heavy, slow-moving time of the star's surface is the most profound journey anyone could ever take. It is a journey that changes the very meaning of the word life. If life is defined by the number of experiences we have, then a life on a neutron star would be the shortest in the universe. But if life is defined by the history we witness, then a few minutes on that star would make us the oldest beings in existence. We would be the silent observers of the grandest show in the galaxy, watching from a seat that never moves, in a time that never passes. As we prepare to transition our thoughts into the interior of this strange object, let us hold on to this image of the frozen traveler. Let us remember that gravity is not just a force that pulls us down. It is a force that holds us in time. The deeper we go, the more we see that matter and time are one and the same. The neutron star is not just a ball of matter. It is a concentrated knot of time itself, tied so tightly that it can barely be undone. In the silence of our vessel, as the light of 1,000,000 years washes over us in a single instant, we finally understand what it means to stand on the surface of eternity. We are no longer just explorers of space. We are explorers of the very fabric of existence. And the story we are reading is one that was written in the first seconds of the Big Bang and will only be finished at the very end of time. As we move our focus from the distorted horizon of time and the shimmering, metallic surface of the star, we must now venture into the interior, peeling back the layers of this cosmic enigma to understand the substance that creates such a profound grip on reality. To understand why time behaves so strangely on the outside, we have to look at the almost impossible nature of the matter on the inside. In our daily lives, we are surrounded by things that feel solid. The chair you are sitting on, the book in your hand, or the very ground beneath your feet all present a sense of permanence and density. Yet, physics tells us a startling secret. Everything we touch is almost entirely made of nothing. An atom is an expansive cathedral of empty space, with a tiny, dense nucleus at the center and electrons orbiting at vast distances. If you were to remove all the empty space from the atoms that make up a human being, the entire population of our planet would fit inside the volume of a sugar cube. We are, in every sense that matters, mostly ghosts. But inside a neutron star, the ghostly nature of matter is abolished. Here, the emptiness has been squeezed out, leaving behind a substance so concentrated that it challenges the very definition of a physical object. If we were to begin a journey into the heart of the star, we would first pass through the outer crust. This layer, about 1 kilometer thick, is composed of a rigid lattice of nuclei, primarily iron, left over from the star's former life. Because the pressure is already immense, these nuclei are packed far more tightly than any material on Earth. The crust is 1,000 times harder than the strongest diamond, a crystalline shell that hums with the energy of the star's rapid rotation. As we descend deeper, the pressure increases exponentially, and the iron nuclei begin to change. The atoms are no longer individuals. They are being forced into a collective existence. Electrons are being driven into protons, and the nuclei themselves are becoming neutron-rich, heavy with particles they would never be able to hold on to in the world of our experience. As we move into the inner crust, we encounter one of the most exotic and beautiful phases of matter ever conceived by the human mind: nuclear pasta. At this depth, the pressure is so great that the individual nuclei begin to deform. They are pushed together so forcefully that they no longer form neat, spherical points. Instead, they stretch and flatten, seeking the most stable shape under the crushing weight of the layers above. Physicists have given these structures names based on their resemblance to common foods because the shapes are so strikingly familiar. First, the nuclei clump into small, round bubbles like gnocchi. Deeper down, they are squeezed into long, thin cylinders that stretch through the star like strands of spaghetti. Further still, as the density continues to climb, these strands are flattened into wide, parallel sheets that resemble layers of lasagna. Finally, these sheets are compressed into a solid block, where the holes between them look like the pockets of air in Swiss cheese. This nuclear pasta represents a state of matter that is millions of times more dense than anything found in our solar system. It is the strongest material in the known universe, far tougher than steel or carbon. It exists only because gravity has seized the atomic structure and rearranged it into a high-pressure geometric dance. In these deep layers, the distinction between a solid and a fluid begins to melt away. We are looking at the transition from a world of particles to a world of pure, unyielding substance. Every millimeter we descend, the density becomes more overwhelming. By the time we move beyond the crust and into the outer core, the pasta shapes have dissolved into a uniform sea of neutrons. Here in the outer core, we reach the point where the star truly becomes a neutron star. The pressure has completely overcome the forces that normally hold atoms together. There are no longer any nuclei, no more lasagna or spaghetti. Instead, the star is a fluid of pure neutrons with a small percentage of protons and electrons mixed in. This fluid is unlike any liquid we have ever seen. It is what we call a superfluid. A superfluid is a substance that has zero viscosity, meaning it can flow forever without losing energy. If you were to stir a cup of superfluid neutron matter, it would keep spinning long after the stars in our sky had gone dark. This fluid can climb up walls and leak through the tiniest microscopic pores because it experiences no friction. It is a quantum liquid where the rules of the subatomic world have been scaled up to the size of a celestial body. In this liquid interior, the density is so extreme that our human analogies begin to fail us. We often say that a single teaspoon of this material would weigh 1 billion tons, or as much as a mountain. But it is not just the weight that is terrifying. It is the absolute absence of space. In this sea of neutrons, particles are packed together so tightly that they are constantly touching. There is no room to breathe, no room to move, and no room for the light to pass. The interior of the star is a place of total, absolute darkness and silence, where the energy of an entire sun is held in a state of permanent liquid tension. The weight of this matter is what generates the immense gravitational field that warps the time on the outside. Every square centimeter of this superfluid is pulling on the fabric of space-time with a force that is billions of times stronger than the Earth's. This is the engine of eternity. The density here is so high that the escape velocity, the speed required to leave the star's gravity, is about half the speed of light. If you were at the center of this star, you would be at the bottom of the deepest hole in the universe, short of a black hole itself. The pressure at this depth is measured in numbers so large that they require dozens of zeros to write down. It is a pressure that could turn a mountain into a pebble in the time it takes to blink. As we move deeper toward the inner core, we enter the most mysterious region of all. This is the heart of the star, a place where the conditions are so extreme that our current understanding of physics begins to crumble. We do not know for certain what exists at the very center of a neutron star. Some scientists believe that the neutrons themselves begin to shatter under the weight. Just as the atoms shattered to form the neutrons may break apart into their constituent components, quarks and gluons. This would create a quark-gluon plasma, a state of matter that hasn't existed in our universe since the first few microseconds after the Big Bang. It would be a place of pure, primal energy, where the fundamental building blocks of existence are no longer bound together, but are free to swirl in a hot, dense soup. Others suggest that even more exotic particles might be born here. They speak of strange matter, a substance that contains strange quarks and might be the most stable form of matter in existence. There is even a haunting theory that if strange matter were ever to escape the core and touch the normal matter of our world, it might convert everything it touches into its own image, a cosmic infection that would turn planets and stars into dense, gray lumps of strange substance. Fortunately, these conditions can only exist in the deep pressure cooker of the star's heart. In this central abyss, we are no longer dealing with the matter of our everyday experience. We are dealing with something far more fundamental, a state of being where the universe is testing its own limits. This transition from the familiar to the exotic is the key to understanding the strange reality of crushed atoms. we see that the universe is not just a collection of different things, but a single substance that can be pressed and refined until it becomes something else entirely. A neutron star is essentially a massive experiment in how far matter can be pushed. It is a place where the fluff of the universe, the empty space within our atoms, has been discarded, leaving behind the concentrated essence of mass. When you realize that the stars, the planets, and the people are all mostly emptiness, you start to see the neutron star as a kind of solid foundation, a point of absolute density that holds the rest of the universe in place. The existence of such a place has profound implications for how we view our own reality. If our world is made of ghosts and the neutron star is made of truth, then our sense of solidity is a beautiful illusion. We live in the thin, light air of a low-density universe, while the neutron star lives in the heavy, true reality of the high-gravity realm. It reminds us that there are layers to existence that we can barely perceive. Just as a fish might not understand the concept of a vacuum, we struggle to understand a place where there is no space between the components of an atom. The crushed atoms of the star's interior are a silent lesson in the diversity of the cosmos. As we imagine ourselves floating in that superfluid sea, surrounded by gnocchi and lasagna made of pure nuclear force, we begin to feel a strange kind of peace. In the interior of a neutron star, there is no change, there are no seasons, no weather, and no decay. The particles are packed so tightly that they are frozen in a state of permanent order. It is a place of absolute crystalline silence. The ticking of the clock, which was so heavy on the surface, might be even heavier here. If time is a measure of change, then in the perfectly ordered heart of the star, time almost seems to have found a resting place. It is the ultimate library, where all the energy of a star's life has been archived in a tiny, dense volume. This density also creates a strange kind of memory. The magnetic fields that are locked into the star's superfluid core are incredibly stable. They are traces of the parent star's magnetism, concentrated and preserved for millions of years. The rotation of the star, its temperature, and its chemical makeup all tell the story of its violent birth. The interior is a record of a cataclysm that happened long ago, preserved in a state where nothing can ever be erased. It is a tomb of a giant, but a tomb that is still vibrating with the energy of the life it once lived. When we consider the strange reality of these crushed atoms, we must also consider the limits of our own knowledge. We have never seen the inside of a neutron star, and we likely never will. Our understanding comes from mathematical models and the study of the pulses that reach our telescopes. We are like people trying to understand the interior of a locked vault by listening to the faint ticking of the mechanism inside. We hear the rhythm of the pulsars, and we calculate the weight of the gravity, but the actual substance remains a mystery. This mystery is part of what makes the neutron star so compelling. It represents a boundary of human thought, a place where our words and our images begin to fail. The fact that such objects exist, that they are not just mathematical fantasies, but physical realities spinning in the darkness, is a testament to the power of gravity. It shows us that if you have enough mass and enough time, gravity will eventually win every battle. It will crush the light, it will shatter the atoms, and it will rewrite the laws of physics. The neutron star is gravity's greatest work of art, a sculpture made of pure matter and distorted time. It is a place where the unseen becomes the only thing that matters, and where the impossible becomes the daily routine. As we prepare to leave the interior and move back out into the twisted geometry of the space surrounding the star, we take with us a sense of the sheer scale of the universe's imagination. We have seen matter turned into food-like shapes of nuclear force, and we have seen liquids that flow without friction. We have seen atoms crushed into a sea of neutrons, and we have contemplated the primal soup of quarks. All of this exists within a sphere no larger than a city, a tiny speck in the vastness of the galaxy. And yet, this tiny speck is heavy enough to hold back the clock and change the history of everything around it. The strange reality of crushed atoms is the final proof that in the universe, size does not matter nearly as much as density. It is the weight of what we cannot see that truly defines the world we inhabit. When we speak of silence in the universe, we often imagine it as a lack of sound, a void where the air does not carry the vibrations of voices or music. But there is a deeper kind of silence that exists in the vicinity of a neutron star. It is a temporal silence, a region of space where the very rhythm of existence has been muted. In this chapter, we must move beyond the physical matter and the crushed atoms to look at the invisible architecture that holds them all together. We must investigate the twisted geometry of space-time, the profound implications of general relativity, and how the curvature of reality turns a fleeting second into a vast stretch of years for those watching from the outside. This is not merely a trick of the light or a mechanical failure of our instruments. It is a fundamental shift in the way the universe is constructed. To visualize this, we must return to the image of the cosmos as a fabric, but we must look closer than ever before. In our everyday experience, we perceive space as three dimensions: length, width, and height, and time as a separate fourth dimension that moves forward independently. But Albert Einstein taught us that these four dimensions are inseparable, woven into a single entity called space-time. Just as a heavy ball placed on a trampoline creates a depression in the fabric, every object in the universe with mass creates a dip in space-time. On Earth, this dip is gentle. It is a soft curve that keeps us pinned to the ground, but does not drastically alter the flow of the seconds. However, the mass of a neutron star is so immense and its size so small that it does not just create a dip. It creates a puncture, a narrow vertical spire in the fabric of existence. This geometric distortion is what we perceive as gravity. When we say that gravity on a neutron star is 200 billion times stronger than on Earth, what we are really saying is that the geometry of space-time is 200 billion times more curved. Near the surface of such a star, there are no straight lines. Even light, the fastest messenger in the universe, cannot travel in a straight path. It is forced to follow the steep, twisted contours of the star's gravity. But because space and time are joined, if space is being stretched and bent, time must be stretched and bent along with it. This is the heart of gravitational time dilation. The steeper the slope of the space-time well, the more time is stretched out to cover that distance. Imagine a beam of light trying to climb away from the surface of a neutron star. It is struggling against a geometric cliff. As it climbs, it must pay a price in energy to move through the warped space. This loss of energy causes the light to redshift, shifting its frequency to a lower, slower vibration. Since we use the frequency of light and the vibrations of atoms to measure time, this slowing of the light's heartbeat is literally a slowing of time itself. To an observer standing on the star, the light leaving their flashlight appears perfectly normal. But by the time that light reaches a friend orbiting far away, The waves have been stretched so thin that they take much longer to pass by. If those light waves were pulses marking the seconds, the friend would see those seconds arriving hours, days, or years apart. This creates a surreal reality where multiple nows exist simultaneously in the universe, each moving at a different speed. It is a concept that challenges our very identity. If you were on that star, you would feel as though you were living through a normal moment. You would be thinking your thoughts, feeling your breath, and watching your watch at a pace that feels correct. But you would be occupying a slow-motion pocket of reality. The deep silence we mention is the result of this temporal isolation. You are cut off from the fast-paced life of the rest of the galaxy. It is as if you are standing in a house where the windows show a world moving in a frenetic, blurred fast-forward, while you remain in a calm, still room where a single candle flame takes an age to flicker. The degree to which geometry can twist time is almost infinite. In the most extreme theoretical models of neutron stars, those that sit on the very edge of collapsing into black holes, the curvature is so intense that the time dilation factors move toward the staggering, while a typical neutron star might slow time by about 30%, meaning 1 second for you is about 1.3 seconds for an observer. As you add more mass, the ratio climbs. We are exploring the hypothetical limit, the place where the star has pushed the fabric of space-time to its breaking point. At this threshold, the cliff of time is so nearly vertical that a second on the surface could indeed represent years in the outside world. This is the region of the deep silence, where the clock is practically frozen in place. What does this twisted geometry do to our understanding of cause and effect? In the Newtonian world we were taught in school, things happen at the same time everywhere. If a star explodes on the other side of the galaxy, it happens now, even if the light takes thousands of years to reach us. But relativity tells us there is no universal now. The sequence of events depends entirely on where you are in the gravitational field. On a neutron star, the now is heavy and stationary. It lingers. If you were to communicate with the outside world, you would find that your hello arrives to your listener long after they have lived an entire lifetime. By the time they send a goodbye back to you, and that signal fights its way down the steep slope of the gravitational well, it might be decades older. Yet to you, it feels like it arrived in an instant. This distortion of geometry also affects the very shape of the star as it is perceived. Because gravity is so strong that it bends light back toward the surface, the star's geometry seems to wrap around its own self. It is a world of mirrors and shadows, where the path of every photon is a complex spiral. This is the twisted reality of the high-gravity realm. You cannot trust your eyes because your eyes rely on light traveling in straight lines. In the deep silence near the star, light is a tangled web. You might see the same star reflected multiple times in the space around it, or you might see the entire universe compressed into a tiny, brilliant circle of light directly above your head. This circle, known as the Einstein ring, is the only portal through which the rest of the cosmos can reach you, and it shows you a universe that is aging at a terrifying speed. The silence of this region is also a product of the absolute stability of the star's structure. On Earth, we are used to change. Winds blow, water flows, and things decay. But the gravity of a neutron star is so immense that it enforces a state of near-perfect structural stillness. There are no landslides on a neutron star. Gravity has already won. There are no ripples in its oceans of superfluid neutrons. They are held in a grip so tight that they move with a crystalline precision. This lack of physical movement is mirrored by the lack of temporal movement. The twisted geometry has created a place that is as close to a state of permanent being as is possible in a universe defined by becoming. It is a monument to the power of geometry over matter. As we contemplate this, we realize that we are looking at the true nature of what we call a force. For centuries, humans thought of gravity as a mysterious tug, an invisible rope pulling objects together. But we now see that there is no rope. There is only the shape of the universe. The neutron star is not pulling on the seconds of your life. It has simply changed the path that those seconds must take. If you are on the star, your time is not being stolen or slowed down by an external hand. You are merely following the only geometry available to you. It is a profound shift in perspective. It tells us that we are not just inhabitants of space and time. We are shaped by them. Our very existence is a function of the curvature in which we find ourselves. This twisted geometry is also the reason why neutron stars are so difficult for us to imagine. Our brains evolved to understand the geometry of the African savanna, where lines are mostly straight and time moves at a constant pace. We have no biological equipment to help us visualize a place where space is a spiral and a second is a century. This is why we must rely on the calm, steady voice of science and the elegance of mathematics to guide us. They allow us to peer into the deep silence and see the logic beneath the chaos. They show us that the universe is a coherent whole, where the extreme conditions of a dead star are governed by the same rules as the gentle gravity of our own backyard. One of the most haunting aspects of this geometry is what happens to the energy of the star over billions of years. As the neutron star slowly cools, its density remains largely unchanged, meaning its gravitational well stays just as deep. While the universe around it expands and cools, and as other stars burn out and turn to black cinders, the neutron star remains a lighthouse of slow time. It is a reservoir of the past. If you could find a neutron star that formed shortly after the beginning of the universe, and you could stand on its surface, you would be standing in a moment that is effectively much younger than the rest of space. You would be a link to the ancient history of the cosmos, preserved by the twist in space-time. This preservation of time is a recurring theme in the high-gravity universe. It suggests that nothing is ever truly lost. It is merely redistributed across the spectrum of relativity. The years that are experienced elsewhere while you experience a second on the star are still part of the same cosmic story. They are just being told at a different speed. The twisted geometry ensures that the universe remains a diverse and multi-layered place where every point in space has its own unique relationship with the passage of the moments. The neutron star is simply the most extreme example of this diversity, a place where the differences are so great that they become visible to our human understanding. As we linger in this deep silence, we might wonder about the ultimate fate of this twisted geometry. If the neutron star were to gain more mass, perhaps by pulling in gas from a companion star, it would reach a point where the geometry becomes so twisted that it can no longer support its own existence. The well of space-time would become infinitely deep, and the spire would collapse into a black hole. At that point, the time dilation becomes infinite. A second on the event horizon would last for an eternity in the outside world. The neutron star is the final stop before this total disappearance. It is the last place where you can still be part of the visible universe while experiencing the maximum possible stretch of time. It is the ledge over the abyss of the infinite. The geometry of a neutron star is also what allows it to be such an incredible laboratory for our understanding of physics. By watching the way light bends around these stars, and by measuring the precise timing of their pulses, we can test the predictions of general relativity with extreme accuracy. We have found that Einstein was right. Space-time is indeed a malleable fabric, and gravity is indeed its curvature. The twisted geometry of the deep silence has been confirmed by every observation we have made. We live in a universe where the ticking of a clock is a fragile thing, subject to the whims of the massive giants that populate the dark. In these quiet moments, as we consider the silent, spinning weight of the neutron star, we can feel the connection between our own lives and the extreme corners of the galaxy. We are governed by the same fabric, the same geometry. The only difference is the degree of the twist. Our lives are lived in the flat, easy planes of space-time, where seconds are brief and the future is always just out of reach. But the neutron star lives in the jagged, steep mountains of the cosmos, where the future is a distant, fast-moving blur, and the present moment is a long and heavy anchor. It is a reminder that there is no single, right way for time to pass. There is only the way it passes here and the way it passes there. As we prepare to enter the final chapter of our journey, let us hold this image of the twisted fabric in our minds. Let us remember that the universe is not just a place where things happen, but a physical structure that dictates the very pace of those happenings. The neutron star is the master of that pace, a celestial conductor that has slowed the music of the spheres to a near halt. In its deep silence, we find a new kind of peace, a realization that even as the universe rushes toward its unknown end, there are places where the beauty of a single second can be savored for an eternity. The geometry of the star is not a prison, it is a sanctuary, a place where time itself is given the weight and the respect it truly deserves. We are merely the observers standing on the edge of the flatlands, looking up at the high, twisted peaks of gravity with wonder and awe, grateful for the glimpse they provide into the true nature of our shared reality. As we reach the final stage of our journey, we find ourselves standing in the long, cooling shadows of a universe that is far older than the one we knew at the beginning of this exploration. The story of the neutron star is not just a tale of birth and gravity. It is a story of endurance. These objects are among the most long-lived structures in the cosmos. Because they are so dense and so stable, they do not burn out or explode like the stars that gave them life. Instead, they simply wait. They slowly leak their residual heat into the void, a process that takes billions upon billions of years. But as we have learned, the passage of those billions of years is a matter of perspective. While the outside universe experiences the slow drift toward the dark, the neutron star itself, and anything that could survive on its surface, exists in a state where time has been preserved in a frozen whisper. To understand the final whisper of these frozen moments, we must look at the fate of the neutron star in the extreme far future of the universe. Current astronomical models suggest that we are living in the youthful spring of the cosmos. The stars are bright, the galaxies are full of gas, and the light of creation is still relatively fresh. But this era of starlight will eventually come to an end. Trillions of years from now, The last of the normal stars will exhaust their fuel and go dark. The galaxies will become cemeteries of cold cinders and silent black holes. In this degenerate era, the only remaining objects of any significance will be the white dwarfs and the neutron stars. They will be the final sentinels in an ever-expanding, ever-cooling dark. Here is where the temporal reality of the neutron star becomes truly profound, because time is moving so much slower on the star than in the empty space around it. The neutron star is, in effect, a time traveler to the end of existence. While the rest of the universe is aging, the star is holding on to its youth. If the expansion of the universe continues to accelerate and the distant galaxies are carried away beyond our horizon, the neutron star remains a quiet observer. It sees the history of the galaxy playing out in a fast-forwarded blur. In its frame of reference, the transition from the vibrant, star-filled universe to the cold, dark, degenerate era might feel like the passage of only a few weeks or months. By the time the neutron star has finally cooled and its clock has ticked forward just a little, the universe it once knew has been replaced by a vast and lonely expanse of cold eternity. This brings us to a fundamental realization. Time is not a thing that exists outside of us. It is merely a relationship between matter and motion. The final whisper of these frozen moments tells us that there is no absolute now. There is only the perspective of the observer. For us on Earth, a second is a fleeting thing. For a neutron star, that same second is a vessel that holds the weight of eons. Neither perspective is more correct than the other. They are simply different ways of experiencing the same underlying reality. When we ask how long something takes, the universe answers with a question. Where are you standing, and how much does your environment weigh? As you rest in the quiet of the night, perhaps you can feel the strange comfort in this. The idea that time can be stretched and held tells us that our experience of the world is not a prison. It is a specific, beautiful window. The gentle gravity of the Earth allows us to experience time in a way that matches our biological rhythms. It gives us a world of seasons, of years, and of lifetimes that feel substantial and meaningful. But the neutron star exists as a reminder that there are other windows. There are places where the rhythm is different, where the song of the universe is sung in a deep, slow bass that never seems to reach its conclusion. It is a cosmic scale that reminds us of the sheer diversity of the dimensions we inhabit. The legacy of these stars is also one of information. Every neutron star contains within its crushed interior the chemical and physical record of its parent star. It is a library of the ancient universe, pinned down by gravity and shielded by the dilation of time. If we could ever find a way to read the data stored in the superfluid cores and the nuclear pasta of these stars, we would find a history of the galaxy that has been preserved with perfect fidelity. Because time moves so slowly there, the entropy, the gradual increase in disorder that usually erases information, is also slowed down. The neutron star is the ultimate archive. It is a place where the moments of the past are caught in a gravitational trap, prevented from fading into the oblivion of time. In the far future, as the universe continues its relentless expansion, these stars will eventually begin to undergo a final, slow decay. Physicists suggest that even the very particles that make up the star, the neutrons themselves, might have a finite lifespan. Over unimaginably long time scales, spanning 10 to the power of 34 years or more, the neutrons may slowly dissolve into lighter particles. If this is true, then even the neutron star will eventually vanish. But because of the time dilation, this decay will take even longer from our perspective. The star will remain as a faint, ghostly presence in the dark, a final monument to the era of matter. It will be the last thing to go, a lingering whisper of a world that once contained light and warmth. But we do not need to wait for the end of the universe to learn from the neutron star. Its value lies in the way it challenges our humility and our wonder today. When we consider that a single second on that star represents years elsewhere, we are forced to reconsider the value of our own seconds. We see that the time we are given is not a fixed currency. It is a fluid, precious gift. Every moment we spend is shaped by the mass beneath our feet and the speed at which we move. In a universe where time can be crushed and stretched, our few decades of life on Earth are not just a brief flash in the pan. They are a specific, unique experience of the cosmic rhythm. The final whisper of these stars is an invitation to look at our lives with fresh eyes. It tells us that we are part of a grander structure, a geometry of space and time that is far more flexible and creative than our daily routines would suggest. We are not just biological machines living on a rock. We are participants in a four-dimensional symphony. The fact that we can even comprehend these things, that a creature of flesh and bone can understand the frozen clock of a dead star, is one of the great wonders of the world. It shows us that while our bodies are small, our minds have the capacity to span the distances of kilometers and the stretches of years. Tonight, as the silence of your room settles around you, try to imagine that silent titan spinning in the dark. It is kilometers away from everything you know, yet it is part of the same fabric that holds your bed and your house. It is a heavy anchor, pinning down the moments of the galaxy. Somewhere right now, as you take a single breath, that star is in the middle of a second that began long ago and will not end for a long time. In that second, the star is experiencing the weight of its own truth, while you are experiencing the lightness of your own. Both are true. Both are the universe. As the neutron star slowly cools, its magnetic fields will eventually fade, and its rotation will slow. It will become a dark, silent ball of degenerate matter, invisible to all but the most sensitive gravitational detectors. But its influence on the structure of space-time will remain. The well it has carved in existence will persist, a permanent scar on the face of the cosmos. Even when the star is cold and dark, it will still hold back the clock. It will still be a place where the present lingers. It is a haunting thought, a universe populated by invisible pockets of slow-moving time, like still pools in a fast-moving river. We have explored the death of giants, the descent into eternity, the reality of crushed atoms, and the twisted geometry of the deep silence. We have seen how mass can seize the ticking of a watch and turn it into a cosmic history. And we have arrived at the realization that time is merely a relative perspective. The final whisper of these frozen moments is not a cry of despair, it is a song of connection. It reminds us that we are all linked by the same fabric. Whether we are in the fast-moving void or the slow-moving gravity of a star, we are all part of the same unfolding story. The neutron star is simply the part of the story where the writer has decided to slow down and linger on a single, beautiful detail. As you drift toward sleep, let the weight of your own body on your bed remind you of the gravity that connects you to the stars. Let the steady rhythm of your breathing be your own personal clock, a gentle pace that is yours and yours alone. You do not need to worry about the years passing elsewhere or the seconds stretching into epochs. You are here in your own now, in a place where the gravity is kind and the time is easy. The neutron star will continue its silent vigil in the dark, guarding the frozen moments of the past, while you move forward into the gentle rest of the night. The universe is vast, and much of it remains invisible and silent. But the more we look, the more we find that the silence is full of meaning. The neutron star tells us that the universe is never empty. It is always full of energy, mass, and the potential for time to be reinvented. It is a reminder that there are always new horizons to explore, even if those horizons are within a single second. Our journey tonight has taken us to the very edge of what can be seen and felt, and it has brought us back to the quiet simplicity of our own lives. We are explorers of the deep silence, and we have found that the silence has a voice of its own. May the image of the frozen traveler remain with you as a symbol of the beauty of existence. May you find comfort in the knowledge that your time is a precious, unique part of the cosmic whole. The neutron star is far away, yet its lessons are close to home. It teaches us that perspective is everything, and that wonder is the only proper response to the mysteries of the sky. In the vast, silent theater of the universe, the curtain never truly falls. The music keeps playing, the light keeps traveling, and the frozen moments keep whispering their secrets to those who are willing to listen. So, let your thoughts settle. Let the heavy, slow-moving time of the neutron star fade into the soft, easy time of your dreams. You have traveled far tonight, through the fire of supernovae and the crushing depths of the high-gravity realm. You have stood on the surface of eternity and looked into the heart of a dead sun. Now it is time to return. The stars above your head are silent, the earth beneath you is steady, and the clock on your wall is ticking at just the right pace for a peaceful night's rest. The final whisper is one of peace. It is the peace of a star that has finished its work and now simply exists. It is the peace of a universe that is vast enough to hold both the frantic pace of the light and the steady stillness of the gravity. And it is the peace of a human mind that has looked into the abyss and found beauty there. Good night, and may your dreams be as vast and as wonderful as the cosmos we have explored together. The invisible clock is still ticking, and the frozen moments are still waiting. But for now, the only time that matters is the quiet, gentle now of your own sleep.